The AIC offers an industry-leading GVM re-rating program for domestic and international customers to world-class standards. From ADR testing, compliance, FEA, federal and state approvals, we take care of everything leading four-wheel drive companies need to ensure their kits are safe for the consumer. The first thing that we do is help our customers understand the vehicle as it's offered by the OEM. There can be up to 20 variants with various changes to wheels and tyres, braking systems, suspension architecture and technology in those vehicles. Then we ensure that ADR compliance is maintained in the vehicle in its modified configuration. So for things like lighting compliance and position, as well as wheel guard coverings, for example, the vehicle dimensions will also change, and that also needs to be taken into consideration. Then we'll go into testing for braking systems, stability control, advanced emergency braking, brake assist systems, for example. The vehicle needs to be assessed structurally to ensure that it is safe and robust at its revised configuration and loading. And then finally, we'll ensure that a vehicle type approval federally has been acquired, as well as the appropriate documentation for state level approvals to ensure that these kits can be applied to new pre-purchase vehicles or in-service vehicles. One of the most critical and certainly the most difficult components of a GVM upgrade is the structural analysis. That's the component where we figure out, is the vehicle capable of carrying this new load in this new configuration? This is important for the end user and the customer's safety, and our customers, the AIC, definitely want to go the extra mile to make sure that they can confirm that the vehicle is safe. To do that, the AIC has partnered with Bremar, and we're joined here today by Brett from Bremar, so thank you for joining us.
No worries, good to be here.
It's been a couple of years we've been working together on GVM upgrades. Bremar has got a history of doing this before the AIC started doing this, but we've definitely been going pretty hard for the last couple of years. So can you give us a bit of a background, I guess, of what Bremar do?
Sure. So Bremar, we're an engineering consultancy based here in Melbourne. We really specialise on the computer-aided engineering and computer simulation side of things, including stress analysis and all sorts of CAE. My background is automotive engineering through Holden, through periods of VZ and VE Commodore, doing a lot of CAD and CAE work there. And since leaving there, I've kind of built Bremar up, and we've got a good core team of guys with automotive OEM experience through Holden, Toyota, Tata, John Deere and GRM, so a really good core team of guys with good experience. And I guess what we're all about is bringing that sort of big company knowledge and experience and tools and making it accessible to sort of small and medium-sized businesses to enable them to do high-level engineering without necessarily having to have the team or the complex software and those sort of things in-house. So yeah, look, it's been great partnering with AIC on these GVM upgrades. As Luke mentioned, we're involved in this space previously, but really since partnering with AIC, we've really been able to step up, I guess, the level of detail and accuracy in our modelling, just with the amount of data and information that you guys are able to provide now. So it's really been able to help us take our analysis and simulation to the next level for these sort of projects as well.
So the first step in this process is we need to know what the car looks like. So it comes into the AIC and we do a complete vehicle teardown and we scan every single component individually and we reassemble that in the virtual space. So then we have a dimensionally accurate 3D scan of every individual part and we send that across to you. And what do you do with that once you get a hold of that 3D scan?
So the first step for us is to we basically build a virtual model of the vehicle that we can drive. It's a full dynamic model that we can drive virtually over any sort of road profile or vehicle manoeuvre, those sort of things. So we will take all the scan data you've provided, reassemble it, and our dynamic model basically consists of the main body of the vehicle, then each individual suspension component, lower control arm, upper control arm, steering knuckles, wheels, the whole lot. We input all the mass and inertia data that you guys have measured as part of the teardown procedure, and then spring rates, damper rates, bushing rates, all that sort of stuff to build a full dynamic model of the car that we can drive virtually and then use in other aspects of the GVM process.
So we've got a virtual vehicle that is dimensionally accurate. It's got all of our three-dimensional bush rates in there, damping rates, spring rates, all the stuff we've measured here, but how do we know that it's actually going to drive the way a vehicle would drive in the real world?
Yep. So this again ties into some of the testing work that you guys do with the RLD collection. So we will then correlate our vehicle model to the physical testing that you guys do at angle C. So we can measure, we take the steering wheel angle, the vehicle speed inputs that are measured from the testing you do, and then we'll look at things like lateral acceleration, roll angles, suspension travels, those sort of things, and make sure that our model lines up with the measured data that you've provided from your physical testing. So it's all about correlating and making sure the virtual model is accurate and is reflecting what's happening in the real world.
So now what we've got is a dimensionally accurate, functioning, multi-body vehicle driving around the virtual space. So now we need to know whether it's strong enough. So what do you need to know to determine how strong the vehicle or the components are?
All right. So I guess when we look at an FEA analysis, the main things we're looking for are firstly accurate geometry. So that comes from the 3D scan data as well as some of the thickness measurements and those sort of things that AIC take for us. We need accurate material data as well. So again, that's data that you're able to provide. We need accurate load data, and then finally we look for some form of correlation with a physical test. It's very easy, well, relatively easy to generate an FEA model and generate results, but understanding how accurate those results are and what level of confidence there is, it's really important to do some physical testing to make sure the virtual model is accurate.
Yeah, and the vehicle components are quite complex. Like a diff housing has got multiple pieces welded together. In the case of some, they're fusion welded. Yep. So that's why the AIC will then go and buy basically a full suite of parts on top of the car that we own, be it differential housing, upper control arm, lower control arm, knuckle, you name it, and all those bits and pieces. And we will physically and destructively test them. So we'll cut sections out and we'll get the material tested to get non-linear material properties, not just its strength, but its profile and its elongation and how that works. But we will then get the component and we'll stick it into the machine or into our hydraulic room, and we'll test it either statically or dynamically. So that might be hundreds of thousands or millions of cycles in an indicative way. So exactly kind of how that part would be tested in the vehicle, restrained, how it would be restrained in the vehicle. And then what we end up with is test results in terms of number of cycles and loads, the strain and yield and fatigue in there, and the failure mode. And we'll present all of that back to you. And then what do you do with all that information?
So basically once we've got our FEA model set up, we'll recreate the physical test that you guys perform. So we'll do that virtually, including the test fixtures that you design and the actuators and the whole lot. So it's as accurate a reproduction of the physical test as we can possibly do. And then we'll take, say, depending how the test is set up, we'll take the input loads that were applied on the physical test and we'll use that as an input to our FEA model. And then we'll be looking at things like strains to compare with strain gauge data from the physical test. We'll be looking at deflections from either the actuator or measured deflection on the test. And from that, we can usually generate a load deflection curve and we'll try and line that up with what's happened in the physical test.
And that's where you'll highlight things like certain welds or stress risers and understand whether that's the failure mode versus failure in the material or somewhere else.
Exactly, yeah, and we can often pick that up. It depends how welds and those sort of connections are modelled, but generally we'll be able to recreate those failure points and load paths, and again, whether it's a static overload test or a fatigue test, the results will vary and we'll be looking for different things. But in a overload test, we'll look at loads and deflections. In a fatigue test, we'll be looking for a failure, like a crack location, and roughly around how many cycles that crack starts to occur, and line that up with the virtual model. There's a lot of factors particularly in a fatigue analysis that we can tune and we need to sort of modify to get it to line up with the physical test. But once we've done that and we've got a good correlation, then we've got good confidence that the FEA results are accurate, regardless of kind of how we set that up for other load cases.
Cool. And then so now we've got a virtual model that is dimensionally accurate, performs like a car, puts the right loads into the chassis and the components that you would get from a road profile. And we know it's going to be as strong as the real world car is, and it's going to fail in the same way that the real world car is. The next one, which is always a hot topic, is what loads is it going to see? Like, what is actually going to happen at the wheels? It's not as simple as just put it up to 4 tons or whatever the number is and say that's it, because it's driving its entire life in different configurations. So the next step from there, I guess, is to understand, what does it see? So what are the common ways to put loads into the vehicle to actually assess a new GVM?
Yep. So I guess there's 2 approaches that we're using at the moment. So the first one is around VSB 14. So This is part of the National Code of Practice for modified vehicles, and within that there's a section where there are some proposed loads for assessing modified suspension components. So that's the first sort of route that we go down, and those loads are defined as loads at the tyre contact patch. So the way we've built our models, we can actually apply the loads at the tyre contact patch. Those loads propagate through the whole suspension system and load up each of the components accordingly. And so we make that assessment based on the VSB 14 loads. The other way, which is a lot more complex but more accurate as well then, is to use our virtual vehicle model and drive that around either vehicle handling manoeuvres or rough roads. We can generate any road profile we need to. And that will generate dynamic loads out of the vehicle. So that really depends on the vehicle mass and the ride heights, the bump stop engagement, spring rates. That takes all of that into account to generate some really accurate load cases, which we can then plug into the FEA stress models and look at either static overload load cases or the sort of time-based fatigue analysis.
Yeah, so that's where the AIC will take our vehicle in an OEM configuration. At OEM GVM, we'll instrument that vehicle with a myriad of sensors and we'll go out to a proving ground, gather a series of different road profiles, different speeds, different load configurations, typically at GVM, and we will bring back rough road, low mu, high mu performance, and we'll get all that information back, which you then use to obviously correlate a life of an OEM vehicle. But then we can also get, because we have that system that's generated and correlated and validated, we can then modify that vehicle to suit a customer's configuration, and then run the same virtual tests again at their GVM?
Exactly, yeah, and that's the beauty of the virtual model. So we know it's a direct back-to-back, so we can, once we've got the OEM vehicle correlated, we can then, add extra ride height, extra spring rate, extra mass, whatever the configuration is that we choose to assess. And we can run the exact same test over the exact same piece of road or the exact same steering input and know that that's a direct back-to-back comparison between the two configurations.
From the AIC point of view, for our customers, we enable them to come up with a road profile configurator, which they would build off of their own experience and their own IP, because if you were going to drive at GVM on the roughest roads that we test on, which there are some very rough roads that we test on, it's probably not indicative of the life of a vehicle. So that enables the customer to be realistic about what that vehicle is actually going to see. And it doesn't always go to plan, does it? So sometimes you'll come back and there'll be issues, there'll be a fail. So, what are the common things that would go wrong and how do we work around that?
We have seen instances where, depending on the weight, spring rates, bump stops, ride heights, all those sort of things, where structural components can be overloaded. So again, this is the beauty of having that virtual vehicle model and suspension system model. We can try different things out. So we can change the spring rate, we can change the damper rates, we can fiddle with bump stop heights and increase the bump stop length to manage the loads and the different load distributions between different parts of the system. So we can do that all virtually and come up with a configuration that we're confident is going to work.
Yeah, so just run the supercomputer overnight with the next revision.
Exactly.
Hope it hasn't crashed in the morning, and then you come back and we make another change.
Yeah.
Easier than testing for a month or two.
Exactly, yeah, and it's certainly a lot of experience and knowledge goes into that. But what it means is, we can essentially change a component, click run, and have a result in a matter of minutes, rather than having to get another spring made, fit it to a car, go back down to the proving ground, that sort of stuff. So really, that iterative, when we do identify those sort of issues, being able to iterate so quickly and come up with a configuration that actually meets the spec is a big advantage of being able to do this virtually.
And so at the AIC, we pride ourselves on a number of things, but typically our scan data is down to like 40 microns accuracy. So we put a lot of faith in that, and we love that. From your side, tell us about the software you use and why would that be considered best in class?
So we use Altair HyperWorks for all our simulation work. So again, this is a kind of a flow on from my days at Holden. HyperWorks is a high-end CAE package which is used by all the major automotive aerospace companies globally. So it's really a high-end package. We really get to control every little part of the model that we want to control, we can. So it gives us a lot of power and input over, how accurately the models are built and how we sort of manage the results and post-processing side of things.
So we've been doing this for a couple of years now, and when we first kicked this off, it was a case of, Brett, how do we do the absolute best industry assessment for GVM upgrades?
Yep.
And I think we've stuck true to that.
Yeah, definitely, and I think it's been a great partnership. It's helped both organisations work to our strengths. As we said, Bremar were involved in GVM upgrades previously, but we were not able to do it to the level that we're able to now in terms of all the data you guys are able to provide and the level of correlation data we can get now. So I think it's been great for us to be able to improve our offering through AIC, and I think, genuinely provide the best in the industry sort of assessments for these GVM upgrades.
Well, I know our customers are very happy. When they receive the report, they're absolutely stoked and know that they've got the best possible assessment. So thank you for all the hard work and to a few more years.
Exactly, thank you.
Cheers.